Hello AP Calc. I am working on slope fields today, section 6.1. This will be the first day of it. What we're going to look at is kind of three typical styles of AP questions that are revolving around slope fields. So here we go. First type of question that they like to ask is to have you actually draw in a slope field for some differential equation. So here's our differential equation. dy dx equals x to the fourth times the quantity y minus 2. To the right here, I'm looking at really a snapshot of a coordinate plane where this location here would be 1, 1, and this location here would be 1, 2. So just a bunch of ordered pairs along here that we are looking at. Matter of fact, what I have 12 dots here. On each of these dots, you're going to be expected to draw in what the slope is at that particular spot. Well, this differential equation will help us do that because this really indicates what the slope is, right, at any ordered pair. And I need my x and I need my y to go in this particular equation. So what I need to do is analyze each and every point, and one way to do that is to look at a table and help you organize your thoughts. So let's start off with this -1 when x is -1. So I would put it into my differential equation, -1, and it gets raised to the fourth, and then I'd have y, which is 3 minus 2. If I calculate this out, I'm going to have a +1 times 1, so I get a slope of 1. At the ordered pair, -1, 3. So I'm right up in this region, right, for this particular location. Now, what did we say our slope was? Our slope is 1. I'm going to get a feel for 1 by looking at the point below it. If I go up 1 over 1, I'm looking at a line that has that type of slope, so I'll just mimic that slope. And all I did was say I'm up 1 over 1, so that diagonal there connecting gives me an idea of what the slope of 1 is, and it makes a nice reference point. So now, I'm kind of smart here, I think. I'm going to figure out that this -1 and getting to the raised to the fourth is always going to be a +1. So basically, I have to focus on the y minus 2. So I'd have 2 minus 2 on this one. That gives me a slope of 0. On this one, I have a 1 minus 2. That's going to give me a -1 slope. And a 0 minus 2 gives me a -2 slope. Let's go fill in the column when x is -1. So we have already got our 1 in place. This has a slope of 0, horizontal line, slope of -1, and a slope of -2, slightly steeper than what I had previously drawn. There we got x equals -1 done. When I put in x of 0, look what happens. It doesn't really matter what goes on with the y parentheses. What is going to get ruled on this one is by the 0 factor. So indeed, this whole column will end up with 0 slopes. So horizontal lines on all 3 of those, or 4 of those. Next, let's move to the 1. Well, 1 gets raised to the fourth. That's easy. These are all going to be factors of 1. 1 times something. And now let's focus on the y. 3 minus 2, 2 minus 2, 1 minus 2, and finally 0 minus 2. And I suspect, well, this will be 1. 1 times 1 is 1. Matter of fact, won't this equal everything that I had in that very first column? So -1 and -2, because it's all getting multiplied by 1, just like it did in column when x was -1. So my slope should look identical to this column here when x was -1. And this was slightly steeper because it was a -2 slope. And that is all that's to drawing in a slope field. You have to take each ordered pair and put them into your differential equation and get the slope. You could go work on problems 1 and 2 now on your homework sheet. So in your packet, you should have something that looks like this. Notice here, this one is not dependent on y whatsoever. The slope is entirely dependent on x. So I could probably do a little bit simpler. What's this over here at -3? I could make kind of a table when it's -3, -2, -1, 0, 1, 2, and 3. I'm having difficulties. When I put in -3, I get -3 plus 1, that gives me -2 slope. When I put in -2, I get -1 slope. When I put in -1, I get 0, and so forth. So I could come over, when x was -3, I had a -2 slope. So a little bit steep. But isn't it true that whenever x is -3, I have a -2 slope? And then when I move to the column when x is -2, those slopes are always -1, so slightly less steep than the one I just previously drew in. Then I go to when -1 and I get 0 slopes, and so forth. So just go ahead and complete that one for the rest of those values. What's interesting to see is when my differential equation is dependent on x, look at how the vertical columns all end up having the same slope. Clever. That's a good thing to observe and keep in your memory. All right, I need to go forward. Problem 2, now notice how this one is dependent on y. So it doesn't really matter what x is, the slope is going to be driven by the y value. So I could make, I suppose, a y column. What do I have? 2, 1, 0, 1, and 2 are the values of y that I need to be focused on. Then the differential will be 2 times 2 or 4, 1 times 2 or 2, 0 times 2, 1 times 2, 2 times 2. Oh, there's some symmetry to that as well. So when y was 2, I get a slope of 4. Here's where y is 2, this horizontal line across there at a height of 2. Its slope is 4. Okay, that's a pretty steep rise. It's going to be up 4 and over 1. So I should have made that probably even more steep. And 4 and 4 and 4 and 4 and 4 and 4. I'll do the easy one. When y is 0, I'm going to have 0, 0, 0, 0, 0, 0, 0, and so forth. What's interesting to note on this particular one is when y is our only driving variable for the differential equation, notice how it's horizontal rows that end up having the same slope. Here they all had zeros. A very nice thing to keep in your memory bank. Another type of problem that they like to have you do is matching exercise. So it could be multiple choice where they give you, here I've got 5 different options for differential equations, and I have one picture here of a slope field where it indicates all the slopes. So what I need to do is try to figure out which one is the one that represents that picture. If I only have an x variable, such as in this one, remember what we saw when we practiced with that number 1? The vertical columns are all the same. Only an x variable, vertical columns where the slope is the same. And then vice versa, when it's a y value, when y was equal to 2, it was horizontal rows end up taking on the same slope. Horizontal rows take on the same slope. So I look at this picture over to the right, and I'm looking for those patterns. Are there horizontal rows, I said that, yeah, horizontal rows, where the slope stayed the same? Well, no, not there. So that just kind of shoots at that. It can't be just dependent on a y variable. So I could immediately toss out e, because I noticed that it's dependent on natural log y. And that looks like the only one that just has a sole y looking at that. Then let's look at vertical columns. Does it stay consistent vertically? Doesn't do that either, does it? So I'm going to rule out A because it was just dependent on X. I'm going to rule out B because it was just dependent on X. So this would be dependent on X only. And I know I don't have those columns of similar slopes. Okay, now we got it down to a 50-50. Another observation that I sometimes might make is which quadrant I'm in helps drive what slope maybe I am. So if I'm in quadrant 1, where things are positive and positive, then in quadrant 1 here, if it's dependent on x and y, wouldn't I expect that all my slopes are positive? So I'm going to go focus right now. Let's grab a different color highlighter here. And I'm going to focus on just quadrant 1. So if I look at quadrant 1, are all my slopes positive? Yes, they are. So now I'm going to go and move to quadrant 2. I know in quadrant 2 my x is negative, my y is positive. So this would result in an answer that would have to be negative divided by positive. So I should see nothing but negative slopes in quadrant 2. So I take a focus on quadrant 2 here, and interesting enough, I don't think that's the case, is it? I have some slopes that are positive, and then I have some slopes that are negative. So I think I've just ruled out D from happening as well. And so I think you could go ahead and conclude that C is it. Check a few, do a few spot checks. Let's just check out, what do I want to check out? 2, 2. So if I put in 2 and I add 2, I get a positive 4. Yep, that's believable. And maybe I go check something, in quadrant 3 and see if I get a negative slope out of it. So that's how I work those. They take a little bit of time, but usually you can eliminate some very, very quickly. The next one, draw the particular solution from the slope field. And remember how these slopes are kind of helping guide our pencil through the slopes. So we're going to draw 2 solutions, one of the solutions that passes through the point 0, 1, and one that passes through the point 0, negative 1. So I want to cut through 0, 1. And I can see here this is 1 and this is 1, so fairly large scale on this slope field, or this coordinate plane. So let's just kind of I got to get in front of this to see. So as I come through here, I notice it kind of does that number, doesn't it? And then this seems to be kind of heading like that. So that was my slope field for that one. For the 0, negative 1, kind of looks like this. It almost looks like there's some sort of asymptote going on through this diagonal, doesn't it? And those are my 2 estimations of what this function would look like. The slope fields kind of guide and will produce the original function for us. Remember, all these slope lines really are supposed to be tangent lines to our curve. So as we draw them, that really is what we're looking for. All right, letter D here. A differential equation, a point, and a slope field are given. Use the slope field to sketch a particular solution through the point. And this time we want to go through the point 0, 1 again. So we're trying to pass through that. So we're going to sketch it, and then we're going to use integration to find the particular solution. All right, so let your pencil do the work here. And I think that's what I like for my slope following. And now what I want to do is let's use integration to undo this derivative. So first thing I'm going to do is separate my dy dx. So I'm going to multiply by dx on each side and swing that dx over. Next thing, let's do an integral on each side. So we're going to integrate the differential y, and we're going to integrate this right side with respect to x. So this will turn out to be y. And over here, the integral will be a natural log absolute value of x plus 2 plus c. And I knew this because it looks like the pattern u prime over u, doesn't it? The derivative of the bottom would be just a 1, And that's perfect. Okay, now, finding the particular solution, we're going to use our point. So at the point 0, 1, we can replace y with 1, and then I can replace x with 0, right there, and add my c. What I'm going to do is figure out what c is. So I'm going to get 1 equals natural log of absolute value 2, which I could delete the absolute values because it is positive 2, and plus c. C looks like it turns out to be 1 minus natural log of 2. So my final particular solution that goes through the point 0, 1 will be a rewrite of that particular equation. All I need to do is get my c written in. So I'm going to have y equals natural log absolute value of x plus 2 plus 1 minus natural log 2. And that would be my solution. Check it out. Put it in your calculator. See if this actually looks like the curve that particular solution turns out to be. And then there's just some good suggestions there on ways to distinguish between slope fields. And I think you can just work on the homework. It's finishing these 6. And then there's a matching exercise. So each of these equations should have a corresponding slope field there. More matching, and I think those two are the final things, sketching and doing that thing. Okay, wonderful. Glad you guys were able to take this in. See you later.